Correct. So previous class we discussed the commutation of this diode clamped multi-level inverter in case of 3-level, right? So now we will go for a space vector modulation technique for this 3-level SVM. So as we already discussed that, so this 3-level is having 3 states. So one is the positive state, 0 state, and the negative state, right? And their corresponding voltages are E0 and minus E. E0 and minus E, right? So that means, so earlier in case of 2-level, you have only positive state and 0 state, right? So now you have 3 switching states, P, 0 and N. So that means, so it will have the matrix. So how many levels you can expect that? So you already discussed that. So number of levels, right? Over the number of switching states. So in case of 2-level, sorry, 3, the number of phases. So how many phases are there? See this number of levels, that is 2, number of phases, that is 3. So 8 levels or 8 vectors in case of 2-level inverter. But in case of 3-level, so you have 3 number of levels and power number of phases. So that means you will get 27 switching states. The same thing if you have 5-level, so that means 3 to the power of 5. So that means you will get around 125 switching states. Okay, right. So here each phase, so among these 27 switching states, we can have we have several classification of those. So after that, how to find out the space vectors? So how to find out the space vectors? The procedure is same as what we discussed for 2-level inverter. So first thing is we need to change this phase voltages or the pole voltages into alpha beta reference frame, and after that, so we need to substitute so their individual values of A phase, B phase, and C phase. After that, you will get the space vectors. All right. So these space vectors, there are 27 space vectors as already discussed. So among these 27 space vectors, so these vectors are of different lengths. So we have the small vectors, medium vectors, and large vectors, and we have this 0 vectors, right? In case of 0 vectors, their output voltage is 0. So that means we have the switch states P, 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 0, 0, 0, or N, 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 right? So what is its meaning? N, N, N meaning is, what is its meaning? What is the exact meaning? N, N, N. So A phase switching state is negative, so that means it will produce minus E. So here it is connected to minus E, and here it is minus E. Okay, so that means from the line point of view, that means the ultimate vector, so output voltage is 0. So this is connected to 0, 0, 0, and this is connected to E, E, and E, E, and E, right? So this is A phase, B phase, and C phase. So this is same as what we discussed, right? So earlier, I think we discussed it 1, 0, 0. So that means A phase. So this is VDC voltage, and here it is 0 voltage, and this is 0 voltage. So likewise, here E voltage or minus E voltage or 0 voltage. And we have the small vectors. So we have these small vectors. Again, the small vectors consist of P and 0, that is one group, or N and 0. It consists of P and 0 or N and 0. So these are small vectors. So we'll discuss here. Right. The first thing is 0 vectors. Okay, it is not shown here. Yeah, 0 vectors. So this is space vector 0. So we have this PPP 0 0 0 and N N N. So this output voltage is 0 and its magnitude is also 0. Right. And we have the next one is P type small vector and N type small vector. So meaning is in case of P type small vector, it consists of P switching state and 0 switching state. So this is P type and this is N type. So this is P type and this is N type. It consists of N and 0. So we have this combination. If you come to this P type, P00, PP0, 0P0, 0PP, 00P, and P0P. Right. So these are the P type small vectors. It consists of P, right? And there is no N in this, right? And we have this N type small vectors. So that is 0NN, 00N, N0N, N00, NN0, 0N0. Okay. Its magnitude is 1/3 VD. Again, it consists of some angle, so same as 1/3 VD into e to the power of j theta. We'll discuss about that angle. It's clear. And we have this medium vectors, right? So we have this medium vectors. It consists of all three. That means it consists of P, 0, and N. So that means P0N, 0PN, NP0, N0P, 0NP, PN0. Right. It consists of 1P, 10, and 1N. So those are classified as medium vector, and its magnitude is 1/√3 VD. Again, it consists of some angle. And we have this large vector, right? It doesn't consist 0. So that means it consists only P and N. So this is PNN, PPN, NPN, NPP, NNP, PNP. Right? All these doesn't consist 0. Clear? And its magnitude is 2/3 VD. Its magnitude is 2/3 VD. So all are obtained from the substituting from the pole voltage. So like we discussed for two-level inverter. So where we first transform that pole voltage into alpha beta transformation. So after that we will obtain each and every vector by substituting appropriate phase voltages or pole voltages. Instantaneous phase voltages we need to substitute, right? Okay. So that means 27 we have. So 27 space vector. So here 3 are 0 vectors. 3 are 0 vectors. Again 12 are small vectors. 6 are 6 medium vectors, and again another 6 large vector. The total is 27, right? So among these, in 12 small vectors, we have 6 p type and 6 n type. 6 p type small vectors and 6 n type small vectors. If you compare with two level, right? In case of two level, you have 8 space vectors. So among 2 are 0 vectors and 6 are some finite vectors, right? Are active vectors. Okay. So whereas here 3 are 0 vectors, but these remaining 24 are active vectors, and among these, so these vectors are of different lengths. These vectors are different length. In case of this one, so what is the length here? What is the length in case of two level? So what is its length? 2/3 VD, right? Its length is 2/3 VD. So here the lengths are different. Its length is 1/3 VD, and its length is 1/√3 VD. And here, so this is 2/3 VD. So that means double. So this large vector magnitude is double of small vector. This is clear? It's clear? clear? So if we keep everything, all these vectors in space vector diagram, so the diagram will look like this. Again, we have zero vectors here. We have these zero vectors. So these zero vectors are placed at the center, right? So that means we have three zero vectors, P, 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 0, 0, 0, and N, 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 right? And we have the small vectors. So starting from V1, so this V1, so this is at an angle J0. So V2 at an angle J 60 degrees, V3 at an angle J 120 degrees. So likewise, so this is V1. Okay, this is alpha axis, right? And this is beta axis. So this is VD by 3. Its magnitude is 1 by 3 VD, right? So VD by 3. So its angle is J0, and this is J60 and J120, and this is 180, 240, and this is 300. So that means we have V1, V2, V3, V4, V5, V6 vectors. So we placed the small vectors. Okay, so we placed the small vectors starting from V1 to V6. So we assume that the zero vectors are V0. Okay, so now we need to place the medium vectors. So medium vector magnitude is 1 by root 3 VD, and its angle is, so that means V7, it is 1 by root 3 e to the power of J 30 degrees. So this is 30 degrees, and this is 90 degrees, right? Again 150 degrees, 210 degrees, and 270 degrees, and 330 degrees. Okay, so we have this up to V12. So this angle is 1 by root 3 e to the power of J 330 degrees. Okay, so we placed the medium vectors in the space vector diagram. So we starting from V7 to V12. So you have V7, V8, V9, V10, 11, and 12. So now we need to place the large vectors. So large vectors and small vectors having the same angle starting from 0, 60, 120, and so on, but their magnitude is double. So small vector magnitude is 1 by 3 VD, and the large vector magnitude is 2 by 3 VD. So this is V13, V14, V15, 16, 17, 18. So up to here. It's clear? So now the space vector diagram is ready. The space vector diagram is ready. So we place the zero vectors, right? Small vectors, medium vectors, and the large vectors. Okay, it's clear, right? So now we divide this one into, this is the space vector diagram, right? The complete diagram. So we have this zero vectors here. So P, 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 N, N, N. So 0, 0, 0, right? Small vectors. So this is small vectors. So we have two switching states, right? Okay, we have two switching states for this small vector, either P switch state or N state, P state or N state. If it is P state, we have P0, 0. If it is N state, 0, N, N. Similarly, here two switching states. So here two, this is another one. Okay, we have some redundancy is there for zeros vector and small vectors. So redundancy is there for zero vectors and small vectors, whereas for medium vectors, so there is no redundancy. Okay, so there is an advantage when you are using SPM for diode clamped multilevel inverter. So normally diode clamped multilevel inverters, so there is no switching redundancy, but if you use space vector modulation, so we can get some switching redundancy for certain vectors. For small vectors and zero vectors, you can get some redundancy. Okay, so we will see what is the advantage or how to use this switching redundancy in later classes. And we have these medium vectors. It consists of all three, that is P switching states, zero switching state, and one switching state. So this is PPP. This is the large vector. Okay, so this is the large vector. Clear? So we have divided this into 6 vectors, right? We are divided into 6 vectors. So that means this is 6 vectors. So this is 1, right? So this is 2, this is 3, 4, 5, and 6, right? So we divided this into 6 sectors. We divided this into 6 sectors, starting from sector 1 to sector 6. So each sector, so it span across 60 degrees. Okay. So again, right, inside this sector 1, right, so this is sector 1. We have this triangle, right? So we have this triangle. So we have this triangle, and this triangle is divided into 4 parts. This triangle is divided into 4 small triangles. So this is 1, 2, 3, and 4. Clear? This is 1, 2, 3, and 4. So that means we have sector 1. We have sector 1. Okay. We have sector 1. And inside that, so you have region 1. Sector 1. So there are 4 regions. So that means sector 1, region 1, region 2, region 3, and region 4. Clear? So these small triangles normally called as regions. Region 1, 2, 3, 4. Is clear? Is clear? So we developed the space vector diagram. So we developed the space vector diagram, right? So we defined the 27 switching states. So among that, 24 switches are active and 3 are 0 switching states. And we placed all those 24 vectors starting from V0 to I think 18 vectors starting from V0 to V18. Again, so this V1 to V7, right? So V1 to V7, not V7, so V1 to V6, right? So there are 2 switching states, that is P type and N type. So we have P type and N type. Clear? It's clear? You have any doubts on this? You have any doubts on this?
Sir, can you please repeat this? The sector 1 triangle.
Sector 1 triangle? These
Triangle,
one?
sir. Yes, sir. Yes, sir.
Okay.
These one.
This is simple, right? See, if you compare with 2 level, right?
My connection is that's why, sir.
Okay. So this is one triangle, right? Okay. This is the triangle. So we assume that this is 60 degrees, right? So we assume that this is sector 1. So we have 6 sectors starting from sector 1 to sector 6. Okay. So in each sector, we divided this into 4 regions. We divided into 4 regions. So this is region 1, 2, 3, and 4. Okay. So this is region 1, 2, 3, and 4. Right. So in later classes, so we'll discuss that what is, for example, if you consider this region 1, right? So region 1, so here, so this, for example, if the reference vector is inside this region 1, so this can be written as 1 0 vector and 2 small vectors, right? In case of it is in region 2, we can decompose that the resultant vector into 1 medium vector and 2 small vectors. Similarly, if it is in region 3, we can the output voltage depends on this small vector, 2 small vectors and 1 large vector. If it is in sector or if it is in region 4, we can means it will be depends on these two, one large, one small vector, one medium vector, and one large vector. Okay, right. So that's why it's divided into 4 regions. Later classes we will discuss that. Is clear? It's clear.
Yes, sir, yes.
Okay. So keep this aside. Right. Right. So next we will discuss the new. We'll come back to this SVM. Right. So next we will discuss the neutral point voltage deviation. Right. So neutral point voltage deviation. So let us assume that this is the neutral point, right? So Z is the neutral point. So assume that the voltage between here to here, so that is Vz. Okay, so that is Vz. So this Vz is neutral point voltage. So Vz is the neutral point voltage, right? So we already discussed that. So we have the applications are different types, right? So one is the active or real power flow applications or reactive power flow applications, right? In case of real power flow applications, so these two, right? So these two DC sources are usually fixed, right? So these are usually fixed DC sources. It may be fed from a 12 pulse converter, or it may be fed from a batteries or some other, right? Okay. But in case of some applications like active power filter or battery energy storage system or something, some other applications, right? So these are actually capacitors. So that means these are replaced with capacitors. So this is an example of active power filter, right? So this is an example of active power filter. So this is AC source, and we have this non-linear load. So the idea of this active power filter is to compensate the non-linear load, so that generate. This is if you ignore this one, right? If you ignore this part, if you consider only this part, right? So here the AC source is connected to a diode bridge rectifier. So this diode bridge rectifier will produce non-linear, or it will produce some THD in the current waveforms, right? So that THD is reflected in the source. To compensate the THD and to make this sinusoidal currents, and it is in phase with the source currents. So we have this. This is entire thing is known as active power filter or D-STATCOM. So we'll discuss this in later classes. So in this, right? So this is 3-level NPC type D-STATCOM. This is 3-level NPC, right? So here, so these are actually capacitors. So these are actually capacitors. There is no DC sources here. So these are capacitors. So some voltage is maintained across these capacitors. Some voltage is maintained across these capacitors. Right. So in case of motor drive applications, right. So these are actually DC sources which are fed from a 12 pulse rectifier. Likewise, right. We discussed right earlier classes. Right. So here, what is the difficulty here? So when you have these DC sources, so when you have DC sources, so we already discussed that in previous classes. In this DZ1 and DZ2, only one diode will conduct, right? So only one diode will conduct. So depending on the current direction, only one diode will conduct, right? So that means if you have this is capacitor, right? If you assume this is capacitor, if this is capacitor, so we have these two capacitors, right? So this is neutral point Z. So this is neutral point Z. Clear? So if we have a positive current, right, so that is flowing away from the capacitor, right? So what is the charge in this capacitor? Will it increase or decrease? If this current is positive, right? So what is the state of this capacitor voltage? Whether it will increase or decrease? The positive current is going away from the capacitor. So what is the state? That means whether capacitor is charging or discharging.
Discharging.
Discharging, sir.
Capacitor is
Discharging.
discharging, right? So with the same thing, if the current, positive current flowing inside this one, whether it is charging or discharging, positive current, this is charging, right? Okay, this capacitor is charging. If it is a negative current, so in that case, so this here it is charging, and in this case it is discharging in case of negative current. Clear? So that means this is point is right. So this is Z. So in that case, depending on the direction of, depending on the conduction of each clamping diode, so either the current is flowing inside this one or away from this one, or flowing inside this one and away from this one, right? So that means, right, so here, so this capacitor voltages are charging and discharging, right? These capacitor voltages are charging and discharging, so depending on the load current direction. If one capacitor is charging, in that case the other capacitor is unaffected, right? Other capacitor is unaffected. Okay, so now our objective is to find out the voltage deviation, right? Find out the voltage deviation in this capacitor voltage. So with respect to, we have different vectors are there, right? Small vectors, large vector, and medium vectors are there, right? So depending on the vector, so which one will affect the neutral point voltage? Okay, which one will affect the neutral point voltage? If this voltage is affected, that means this Vz is varying, right? That means it's supposed to be constant, and it is must be equal to this one, right? If it is varying, so in that case the output levels, that means positive we will get some this much of voltage, and negative we have some different type of, means some different magnitude. Okay, so let us discuss the effect of neutral point voltage, the effect of neutral point voltage on this effect of neutral point voltage with respect to different space vectors. Okay, so first we consider zero vector, right? So first we consider zero vector. So we have zero vectors are P P P, so 0 0 0 and N N N, right? So assume that, so this is three-phase load. Assume that, so this is three-phase load. Okay, so that means this is the DC source, or this is the capacitors, and this point is Z. So we assume that, so this is VZ, that is neutral point voltage, right? So we have these three phases. So say it is A phase, right, B phase and C phase. Clear? A phase, B phase and C phase. So now the question is, if it is PPP, right, if it is switch state is PPP, so how this load is connected? This means the capacitors and this load, how it is connected? What is the meaning of PPP? What is its meaning? So P is
Top switches are on.
A phase, it is connected to E, right? Okay, so A phase is connected to E, so this is connected here. Okay, so B phase is also connected to E, and C phase is also connected to E, right? A phase, B phase, C phase, both are connected to E. Clear? So here, if you notice that, so what is happening here? Is it drawing any power from the source? Is it drawing any power from the source?
No, sir.
It is not drawing any power, right? So there is no connection here, right? So there is no connection here. So that means it is not drawing anything from the source. So that means the source is short circuited. So therefore its voltage is 0. Therefore its voltage is 0. Clear? Similarly, if it is a 0 switching state, so all this A, B, C are connected to this Z. If it is an N switching state, so all these A, B, C are connected to this point, right? So all these are connected to this point, right? So all these cases, it is not drawing anything from the source, and the source is short circuited. So that means it is producing a 0 voltage. So that's why these are known as 0 vectors. Here. So now the question is, so in this 0 vector, so will it affect the this voltage Vz, this neutral point voltage Vz? Is there any effect on this neutral point voltage Vz? So with this one,
No, sir.
is there any effect on this? So by operating the inverter like this ABC, if it is short circuiting the load, so will it affect the neutral point voltage? Simple question. So there is no physical connection to this neutral point, right? So whatever the voltage there earlier, the same voltage is maintained. So that means it will not affect, right? It will not affect the neutral point voltage. This is clear? This is clear?
Yes, sir.
Okay. So again, so next one, we have this small vectors, right? In case of small vectors, we have two types, right? So one is p-type small vector and n-type small vector. So we'll consider one p-type small vector. So we have p-type small vectors, different small vectors are there, right? So just consider this p00. So consider p00. So example, so p00. So we have this load here. So we have these DC sources, and this is the neutral point Z, and this is VZ. Okay, so this is A, this is B, and this is C, right? So how this P00 is connected to the load? So A is connected to this positive, right? Okay, right. So this B is connected here. So B is connected here, and how this C is connected? C is a 0, right? So that means C is also connected to 0. Clear? C is also connected to 0. Is clear? Is clear?
Yes, sir.
Okay, right. Okay, so now load is actually connected, and the load is feeding from this DC sources or these capacitors, right? So now how with this neutral point is affected? So how this neutral point is affected? Right. So whether this, that means this capacitor is feeding this load, right? So that means the top one is feeding the load and the bottom one is not connected, right? The bottom one is not connected, right? So now whether it is charging or discharging, that this top capacitor is charging or discharging, so that all depends on the load current direction. Okay, so assume that the current direction is like this. So assume that the current direction is like this. So that means, so this is the outgoing current. So this is the outgoing current. So now tell me, so this capacitor, the top capacitor is charging or discharging?
Discharging.
Discharging, sir.
Discharging.
Discharging, right? This capacitor is discharging. Clear? Okay, right? This capacitor is discharging. So we have this control mechanism such that these two DC sources must be equal, right? So these two DC sources must be equal, and equal to some reference value, right? So that means these two DC capacitors are equal to some reference. Okay, so this is the fixed one. So here also, in case of this is where we have, right, the voltage across this DC bus is controlled, right? The voltage across this DC bus is usually fixed, but these two inner capacitors will vary. For example, this entire thing is 600, for example. So ideally it should be 300 and this should be 300, right? This is 300 and 300. For example, if it is changed to 280, so in that case this is changed to 320. Okay, so this one is changed to 320, but because of we have outside controller, so that will keep these two DC sources some equal to some reference value, right? Clear? So that means one capacitor is increasing or decreasing, so that means the other capacitor is in the opposite action. Clear? So that means in this case, if it is connected like this, right? So what is the voltage? This VZ. If one capacitor, this is C1 for example, this is C2. If C1 is discharging, what is the state of the C2? Or in other words, what is this VZ? Whether it will increase or decrease?
Increase.
Increase.
Will it increase or decrease? So this capacitor is discharging, right? So that means the voltage in this capacitor is reducing, right? So we assume that the sum of these two voltages, that is VC1 and VC2, so both are equal, or it means both are, the sum of these two are equal to this fixed DC source. So in that case, obviously this capacitor VZ voltage is increases. Agree? Clear? So this capacitor voltage is increases. It's clear? Clear? So for example, if the current direction is reverse, this is for positive current, right? So this is for positive current. In case of negative current, that means in case of regenerative, what will happen? In case of regenerative, so this direction of this current is, if it is the direction of this current is something like this, so in that case, this capacitor charging, right? So that means top capacitor is charging, right? So therefore the bottom capacitor, that means VZ, is decreases. It's clear? So positive current, the neutral point will be increases with p type small vector, and for the negative current, the neutral point voltage will be reduced with negative current. Clear? So now we'll consider n type. So n type vector. So we have different n type vectors are there, right? So what is that? So 0 n n. So there is the first n type. Consider this is 0 n n. Okay. So we have this load 3 terminals. So this is A, B, C. So how this 0 and N is connected? So how it is connected? So this point is, this is Z, right? So this point is connected 0. That means it is connected to Z, right? So N means it is connected to this negative. So here also this is connected to negative. Okay. So this is the neutral point current IZ, and this is its voltage VZ. Okay, its voltage VZ. Clear? So assume that the current is flowing in this direction, right? The current is flowing in this direction. So now what will happen? So that means this is connected, this capacitor is connected to this load, right? The bottom capacitor C2 is connected to the load. So now what will happen? If it is a positive current, What is the state of this Vz? What is the state of Vz in case of positive current?
Decreases.
This Vz is decreases for positive load current, right? In case of negative current, in case of negative current, in case of negative current,
Increases.
so negative current means this capacitor is charging, right? So that means this Vz is increases. It's clear? It's clear, right? If you compare with this one, P type, right? For the same positive current, right? For the same positive current, so this is N type, right? So in case of this P type, if you write side by side here, for the same thing, so this Vz increases and this Vz reduces. Okay, Vz increases and Vz reduces. So what you understand that, so for positive current, right, for positive current, P type, right, P type vector increases the neutral point voltage and N type vector reduces the neutral point voltage, and vice versa for the negative current. So that means what you understand that, so P type vector, if it is increases the neutral point voltage, N type vector is trying to reduce the neutral point voltage, right? But the output voltage that produced by the P type and N type, so both are same, right? So what you understand that, so we want to keep this Vz almost constant, right? So we want to keep this Vz constant. So that's why when it is constant, so in that case, both these capacitors are equally charged. So therefore, there is no DC offset in the output voltage. Clear? Right. So that means we can effectively use these small vectors. One time, if you want to increase the neutral point voltage, we can use the, for example, simple example, I'll give you. Right. So this is Z. So assume that at some point of time 290. So this is 310 volts. Okay. So this is connected to some 600 volts. Okay. So assume that the current is positive. Assume that the current is positive. Right. So assume that the current is positive. Okay. So now in certain time, so we observe that you need to apply some small vector, right? You need to apply some small vector. So among this P type and N type small vectors, so which one you prefer? So which one you prefer? So which one you will prefer?
N types.
You want to apply a small vector, so which one you will prefer in this certain case? What is the best option?
N types.
Yes, please.
N type.
N type, sir.
N type, right? So just we go through this, right? So this one is, this Vz is more, right? That means this capacitor voltage is more. Okay, so that means we need to reduce this Vz. This is the voltage, right? We need to reduce this Vz for positive load current. So that means come to this table. So the load current is positive. So if you apply N type, this Vz is reduces. If you apply P type, this Vz is increases. So that means we need to apply N type small vector here. We need to apply N type small vector, right? By mistake, if you apply P type small vector, what will happen? So this gap further increases, right? If you apply that, so what will happen? It may be further increase. It may be going beyond this 310. If you apply that, it may be reduced to maybe 300 or 305 or something. That gap will be reduced. It's clear? It's clear. So this is the point. So where we use this p-type and n-type small vectors in space vector diagram. Okay. So the idea of this using this p-type and n-type is to balance these two capacitor voltages. Right. So this ultimately we are balancing these two capacitor voltages, right? If these two capacitors are not equal, so what will happen? So this positive one will produce 290 volts and this negative one will produce 310 volts. So that means you will get some DC offset. So to avoid the DC offset, so we need to balance these. Clear? Clear? So we'll discuss more on so how to use this p-type and n-type. So next we have this medium vectors. So we have these medium vectors. So one example of this medium vector is N0P, right? So N0P or P0N, both are same. Just to draw it easy. So we have this DC source. So we have A phase, B phase, and C phase. Right. So how this P0N is connected? So how this is connected? P0N. So P, right? So this is connected to A. So this is connected to 0 and this is connected to N. Right? So this is C1 capacitor and C2 capacitor. So you assume that this current is positive. So this current is positive. Clear? So assume that so this current is positive. So now what is the state of this VZ? So what is the state of this VZ?
Increases.
Increases or decreases?
Increases.
Increases.
How it is increases? See earlier, if you notice that, right? If the current is flowing like this, right? The outgoing current is flowing this one and this way, right? Okay, the outgoing current is flowing so in this direction and so in this direction. There is no option, right? Okay, clear. So that means it must be flow like this. So that means it must be flow inside this one. So therefore this VZL is increasing or decreasing, right? So whereas here, right? So here this current is flow like this, okay, and this current may be flow like this, or it may be flow like this, or it may be flow like this, right? So we are not sure, right? So all these are so depending on the instantaneous values. Okay, if the C phase current is more, so in that case this B phase current is negative. If the C phase current is less, in that case the B phase current is positive, right? So that means you are not sure whether the current is in this direction or in this direction, because it is also depending on the magnitude of the C phase, right? So that means, so in this case we cannot justify so whether current is, means this voltage VZ is increasing or decreasing. So this is undefined. So this state is undefined. So why it is undefined? So earlier case the outgoing current is passing through only one point, right? So now this outgoing current is distributed to B phase and C phase. So therefore the magnitude of that current is depending on the magnitude of the current. So either this B phase may be positive or negative, right? So there is a chance that this B phase is maybe positive or negative. So that all depends on the C phase. Is clear? So that means either the capacitor is charging or discharging without thinking of means without knowing that can be determined. So only when you know the status of or when you know the magnitude of C phase. So that means so these vectors are undefined. Okay, so whether it is increasing or decreasing the neutral point, so that is undefined. So definitely it is affecting the neutral point, right? So definitely it is affecting the neutral point voltage, but whether it is increasing or decreasing, so that is undefined, right? So in this case, the neutral point, in case of small vectors, the neutral point is affecting, and it means we are know that whether it is increasing or decreasing. In case of zero vectors, the neutral point is not at all affected. So now large vectors, okay, so large vector, so we have this diagram. A, B, C, right? So one large vector, you may consider P and N, right? So already discussed that large vector will not consist of any zero state. So how this P and N is connected? The P positive, N, so that is connected to this negative, and this is connected to this negative. Okay. Is clear? So this is C1, C2. So now we assume that this is the current direction. So assume that, so this is the current direction. So assume that, so this is the current direction. So now, what is the effect of this jet? What is the effect of this jet? So how this jet is affecting now?
Increases, sir.
Z will increase.
How can you say it is increases?
VC1 will decrease, sir. So VC2 has to
How
increase.
exactly VC1 is decreases? So in this connection, there is no jet point is not connected anywhere, right? So that means the C1, C2 are in series. Okay, C1, C2 are connected in series. So now how can you say that this VZ is affecting? So what is the current direction? If this is the current direction, the current is flow like this, and this is flow like this, and it will flow like this, right? Okay, so combinedly C1 and C2, so both are feeding, right? So both are feeding the load, right? Combinedly C1, C2 in series, so both are feeding the load. Whatever, right? So whatever the charging and discharging, so both are same, right? If it is charging or discharging, so both are same. Clear? So there is no current that is flowing through this one. When there is a current flow in this one, right? So in that case, so only the problem will occur. So either this current in flow in this direction or the current flow in this direction. So then only this VZ will be vary. Okay. If the current is flowing inside this capacitor, bottom capacitor or upper capacitor, so then only the neutral point problem will occur, right? The two capacitors are connected in series, so both are feeding the load. So in that case, there is no chance of this neutral point, right? That means the neutral point voltage will not affected. So both are simultaneously charging or simultaneously discharging. If it is in this case, so both both capacitors are simultaneously discharging. If the current is negative, in that case, both capacitors are simultaneously discharging. So in this case, there is no effect of VZ. Clear? So whenever there is a current flow in this VZ, if the current flow inside this one, right? So there are two options. Either the current will go here in this direction, or the current will go in this direction. If this is the direction, so in that case, this capacitor is charging. If this is the direction, this capacitor is discharging for positive current. Okay, so negative current, the scenarios are interchanged. Is clear? Is clear? So in this case, so both capacitors are in series, right? So both are feeding to the load. If you summarize this one, so we have this zero vectors and large vector will not connect to any neutral point. Zero vectors or large vector will not connect to neutral point, right? Therefore, it will not affect the neutral point voltage Vz, or in other words, it will not affect the capacitor voltages. In case of small vectors, right? So p type and n type. So with this p type, maybe this neutral point voltage may be increased or decreased. That means these are affected by the Vz. And we have this medium volt vectors. So medium vectors are actually affecting the neutral point voltage, right? So medium vectors are affecting the neutral point voltage, but whether it is charging or discharging, or this Vz is increasing or decreasing, so that is unknown. Clear? So zero vectors, so not affecting this one. So p vectors, Vz affecting, but their action is, that means p type and n type, their actions are opposite. In case of medium vectors, it is affecting the neutral point voltage, but whether it is changing or it is increasing or decreasing, so that is unknown, right? Or in other words, you require to analyze it more to obtain whether it is changing, I mean whether it is positive or negative. Clear? So you have any doubts on this? So you have any doubts on this? Right. See, in many applications, you may have doubt that why. So these two should be constant, right? The sum of these two capacitors must be constant, right? So our idea is to control that individual capacitor voltages, right? So this sum must be constant, right? For example, this is 600 volts. The sum of the two capacitors must be constant, but the difference we need to make sure that, so that must be constant, right? That means the difference must be equally divided. You must get 300 on the top capacitor voltage and another 300 on the bottom capacitor voltage. If this is changing, right? So obviously the inverter output is also changes. You have any doubts on this? Okay, I will wind up here. So in next class we will continue this SVM, right? You have completed that assignment, not assignment, minor one.
Hello, sir.
Yeah.
Sir, I am facing problem, sir, in push-pull converter, sir. For
Just a
designing
minute.
from
Let me
12
stop
volt
this
for
recording.
15 volt, it is not possible,
Just a
sir.
minute.
Hello.
Just a minute. Let me stop recording. So where is that option? Okay, tell me what's your doubt?
In push-pull converter designing, sir, I from 12 volt source, I maximum I can get up to 80 volt only. I can't able to get 415 volt.
So for
If I
push-pull
am going
converter,
for
you need to tune the transformer. Okay.
what, sir?
You need to tune the transformer beforehand. You turn off your speaker. Okay. So in push-pull converter, you need to tune the transformer, because in